Okay. Good morning, everyone. My name is Reem Aboukhaddour. I'm the cereal pathologist at Agriculture Agri-Food Canada, and usually every year I talk about like a couple of disease diagnosis and management. However, today I've changed a little bit of the plan. We're gonna talk about our disease nursery and what factor it takes to establish a successful disease nursery and why we do it. However, before I talk, I like to acknowledge and thank my crew who actually help this part being done. And I have here our senior tech, Eric Eminson, who actually coordinate and carry most of the co-op trial. And I have beside him Therese Despens. She is the Bunt. She takes care of the Bunt nursery, which is the most challenging and difficult disease to rate. And we have our co-op student, Olivia and Nadine. And I have my biologist also who joined recently, Kaveh. He's walking. I didn't see him. He will come and talk about race characterization too. Okay. So I control two of wheat nursery diseases, the stripe rust and the common bunt. And to give you a little bit of idea about disease on wheat in Canada, in Western Canada actually, there are 5 diseases that are regarded as a 5 top priority by the registration trial. So for any cultivar to be registered, it has to pass 5-year testing against those 5 diseases. So the 5 diseases are common bunt, fusarium head blight, and the 3 rust, stem, leaf, and stripe rust. Now, in Winnipeg and east to Saskatchewan, naturally, the stem and leaf rust occurring beside the fusarium head blight. So you will find the nursery for those diseases in AFC Canada around that area more than, or previously was in Winnipeg. And for stripe rust and common bunt, they actually naturally like to occur more, or severity is in the region of the Pacific Northwest and its extension in Alberta and BC. So it makes sense to have those 2 disease nursery here at Lethbridge. What you see behind me is actually our winter wheat nursery for both the stripe rust here and the common bunt there. We have our spring wheat nursery for the both diseases as well in different locations. We have here about 2,000 lines for each, the stripe rust and the common bunt. And these lines come from all different breeding programs across the West. Now, to establish a disease nursery, you really we think about it as a pathologist point of view. You have to bring the 3 factors together to get a disease. So you need the pathogen, you need a virulent pathogen, you need the host or the plant, the susceptible plant, and you need the conducive condition to have it. If we wait for natural infection, it's really hard sometimes because you might get the inculum at time, you might not. So for disease nursery, we try to create the best condition to bring these 3 factors together. We have our trial designed in a way, we have checks, what we call checks. And those are lines that are known to have a variation in reaction to the disease. Let's say in this case, I'm talking stripe rust. So we have the lines that are susceptibles, the line that have intermediate reaction, and the line that are resistance. Those are kind of a standard in your test. It tells you whether your experiment went right or wrong, or you put the plants under enough disease pressure. And we can introduce these lines so often. We have measure check and minor check, and the measure check are introduced every 10 to 20 lines, I think, and the measure one every 60. Or they repeat all together through all the trial. So they are very distributed evenly, and it's a way to guarantee that our testing is right. Now, if you walk after this talk, I think you're gonna go to RoboPlots. In RoboPlots, you will not find rust because this year the rust came late and didn't overwinter, so naturally infection didn't happen yet. But in this our disease nursery, you will find it, because Eric has actually went and infected those plots early enough after the first rain where the weather was conducive. And for stripe rust, it needs a combination. For any fungus, you need enough moisture for the infection to happen. And with the stripe rust, it's like the cool kind of weather. So you have to catch that weather and apply the infection or the inculum, I would say. And I would like to just show you the symptoms of one of these. Thank you. So you would see this orange color, Eurydiaspore. These are actually the inculum of it, and it forms on the leaf. It forms as a stripe. However, on the lower or like early leaves, it doesn't follow the shape of stripe. On the older leaves, it forms the stripe shape, and that way it's called stripe rust. And if you pass your hand over it, it will get like orange color. So if you walk in very infected, heavy infected field, you will get like even your boots or your pants color orange after. So what we do artificially, we actually collect the inculum from the field, and then we take it and increase it. We save it in our -80, and then when the growing season, we plant our nursery. And the planting date has to play with it. We try to plant as late as possible, because we want to avoid that the plant get dry before we get the infection. It's very hard to get infection on already maturing plants. So we try to keep the plant greener as much as we can, and we provide as much as moisture. Now with the inculum that we collect from the naturally infected plots from the previous season, we store it, and then before the season, before when we want to inculate, we increase the inculum inside the growth chamber on susceptible plants. It takes about I think it took you about 1 and 1/2 gram of these spores to be collected, and we mix it with talc in a ratio 1:30, so 1 gram to 30 gram of talc. I can pass these leaves around, and you guys are free to walk. And actually, yeah, that's fine. And we mix the inculum with the talc, and then we have the whole plot actually surrounded by spreader or by the susceptible line. So Eric go and concentrate spraying on the spreader, and actually it falls nicely, like almost as a, as a cloud of spore. And I like it so much, I play around with it, and I'm gonna play a little bit more. You see how much, and the spores are so light. Stripe rust is a wind-borne disease that can travel thousands of kilometers, yet it is still can be viable. So the spore germinate. It just needs the moisture to germinate. And after the germination and infect the plant, it takes about 3 weeks before you see the symptoms. And then hopefully with the dry, with the wind and the dry weather, the spores get carried out to infect the rest. And that's how we do it. I'm just gonna try this one more time for fun. I see people wanna see that. Nice. It is nicer on a cloudy day after rain. There you go. Otherwise I will keep playing around. And so before I talk about the other disease, which is the common bunt. Now, you realize the stripe rust. So I mentioned 5 priority diseases that any cultivar has to pass to be registered in Western Canada. I would say among the 5, it's only the stripe rust and the fusarium head blight are still the kind of like the threat, or not the threat, the disease that occur and cause damage today. However, stem rust, leaf rust, and common bunt are still threatening. They don't cause damage yet because we have been so successful in breeding resistance for those diseases over hundreds of years. Common bunt is actually one of those, I call them like almost historical historical diseases, but we still consider them priority. We have a huge history with those diseases that they are known to be so damaging that we cannot let the chance to get loose on the standard of resistance, because they are still, and they can still cause damage if you just ignore that. Common bunt is one of those diseases that actually started when Canada started, basically, with the first time they grow wheat. It was more in the east before people reached to the west. In the 1850, they already knew it. They dealt with it in the east, even like it was around the 1850, it was actually illegal to sow any bunted disease, any bunted seed into the ground. Then when wheat start to expand on the west, they copy the practices to control common bunt from the east. Common bunt is a seed-borne disease, and I don't know if you have ever seen it. I have some samples. So this disease is not like rust. It's a seed-borne, it's not a wind-borne. It is called cover smut or stinky smut for a reason, because it's a stink and it's covered. It's not easy to see. And it takes very good trained eye to read those lines that insulated with bunt. Therese take control of that. Therese disappear. She's shy in the back. Wave your hand, Therese. Wave your hand. Okay, Therese take control of this, and she read them, and I hope she gave me the bunted head yesterday. Yeah, they are here. So what happened, the fungus, the spores actually on the seed, on the outer side of the seed, on the surface. If the seed is contaminated with this disease and you put the seed into the soil, and then with a cool condition, the fungus will germinate. You can distribute this, yeah, let them smash it. The spore germinate, it will infect the emerging seedling and will grow with the growing tip of the plant. And then instead, and it, like you don't see it until like the heads start to form. And then instead of your grain, you will get a bunted mass of black spores. And Therese is showing that, and it has a stinky smell. I don't have any bunted seed here. But if you smash the seed, it will. Here, Therese, come to the camera. Show it. So that's the bunt spores, and it's literally called the bunt ball. So it's sabotageous quality. So
there are a few seeds in there. They are shriveled, but the rest is full of spores. Sometimes the whole head will become infected, sometimes more one side. But it's usually dwarf bunt that travels up one side of the head. Common bunt usually goes on both sides, and sometimes it's just the bottom florets. But stinking smut.
So thank God for seed treatments to control this disease, which was like a huge issue in the early 80s, more than before stem rust become an issue. Yet it's so dangerous because it sabotages your quality. Like we have a standard, if one head among 1,000 head, like the car lot will be rejected. It's not even desired by feed lot because animals don't like to eat it. So it's like you almost wasted. So that's why we have to breed for resistance, because as much as seed treatment is effective and have actually reduced the incidence of it, yet not all the time seed treatments are effective under all conditions. Not all the time people are using seed treatments. With the growing organic farming somewhere, it's like it might be an issue. So that we have high standard of breeding for this. And usually the rating of the bunt, I want you to explain a little bit about challenge of rating the bunt and how you do it. Therese, run away. Okay, usually you kind of want to rate it before you see before the plant getting so mature and dry, because it's hard to see it. Almost when like your head is kind of green, and then you cannot really see it because it is covered. So the outer shell of the seed is there, but instead of the grain you have that black mass of bunt. So you have to go and look for it carefully, and you have to kind of do it in a shady day, in the early part of the day, because under the sun you cannot get that reflection, you cannot distinguish the color. So that's how it is done. However, I didn't talk about stripe rust rating, which is kind of straightforward. It's way easy. We can rate this very fast, like almost if we take this 1 hour, Therese will take that 10 hours. For stripe rust, if you go and look around, it just we take how much of the leaf is actually covered with those orange pustule, and we just give it a rating, and that's it. And based on our check, we can then judge the rest of the line, whether they are more in the range of intermediate, more of the resistance, and etc. etc. We take all that result and we go to the meeting for the registration trial, and we vote on those cultivars for the disease committee. Now I want to introduce Kaveh, Dr. Kaveh Gambarnier. He's the biologist who joined my lab recently, and he is helping us immensely in getting the race characterization, which is other part we do in our research. So we do the nursery, but then we do something else which is called like the race characterization, and the rust pathology, it's fundamental part of any rust pathology. We have doing that for hundreds of years for stem rust and leaf rust, and it is very important because rust has the ability to change its virulence spectrum. So it reacts to different, it has a specific interaction with the plant. So there is something like a virulent in the pathogen, virulence gene, and there is something else in the plant matching that, the resistance. So if that combination, if that combination break, you might have disease, So it's like that specific reaction. So what we do, we collect the different isolate from the field, like we go naturally collect the stripe rust, and then we have to purify it, and then I will let Kaveh show you and explain a little bit about the process. It's just a way to communicate what resistance genes are still valid and what resistance genes are broke.
Thank you, Reem. Hello, everybody. It is my magic box. I brought it here for you to what we are doing here. As Reem said, one of the problems that we have with yellow rust is that we have a different races. So in general, in most pathogens, we have a different races. But for some pathogen like a yellow rust, these different races are very, very important. Why it is important? Oh, okay. Why is it important? Because the problem with them is that every year or every second year or every third year, we got new races. So the commercial cultivar or lines that we have, probably there will be no longer resistant to these new races. So one of the main things that we should do at the beginning, one of the goals that we have here is that we should monitor the races that we have in the fields. So in different locations, especially in yellow rust in southern Alberta, we have a problem. We should find out that which kind of the races we have first. And then we can go to the next level. So first question is that how we can find out the different races. One of the methodology that we're using differential lines. These differential lines that we're using here is about 20 of them, and each one has one specific resistant genes. So based on these differential lines, we can inoculate the isolate that we got from fields. Then we can figure out, based on the reaction of this differential line, we can find out which races we have. When we find out which races we have, then we should go to the next level. So the next level will be that what is our commercial cultivar reaction to these new races. So if we find out, for example, 100, 200, 300 commercial cultivars, some of them are resistant, some of them are susceptible, then we can do kind of the playing game with the pathogen. As a matter of fact, as long as the pathogen shifting his races, by shifting the cultivars that we're using, the ones that are most resistant to the new ones, we can play with the pathogen. So it is a kind of the long-term playing game with the pathogen population in the field. So it is one of the main goals that we are doing here. So it is the first step that we are doing. So it is the start of the experiment. So we find out that which races have. Then hopefully in the future, when we find the races, we inoculate the commercial cultivars. Then we find out which lines, which cultivars are resistant, which one are susceptible. Then we can go for the next step. But the problem with the this differential line is that inoculation and rating of these differential lines takes time. It's about 3 weeks to 4 weeks, 1 month. So it takes 1 month to find out the race of a pathogen, and it is very long term. Well, another goal that we have here is that we shorten this time. So we're trying to find a kind of molecular markers that develop in our lab. Then we can bring these 20 or 20 days or 1 month to almost 1 day. So in 1 day, we can recognize the races of the pathogen. So the fastest, the better. Then it is, as I said, the next level will be the inoculation of the commercial cultivar to find out which one are susceptible, which one resistance. Then the next level, that maybe it is the final goal, is that developing a kind of the lines or cultivar that can be resistant to most of these races. So by now we find out that at least 4 of these differential lines are completely resistant to most of the races in southern Alberta. And it is a good news. So imagine if we can have these 4 genes in one line. So in this case, you can have a kind of the line that can be resistant to a wide range of the races in the southern Alberta or even in Canada. So it is a very brief explanation of what we are doing here and what we have started. And I think Reem and Eric here done a lot of work to set up this experiment, and hoping that we get a good result. Thank you.
He can show you a little bit later on. The only comment I have to say, we are very recent history in compared to other countries. Here in Canada with the stripe rust, we are very recent history with research on stripe rust actually. So we are almost in the infancy stage in compared to stem rust, which we have or leaf rust, which we have hundreds of years. So we are building the capacity, to be honest, to do this. So we are really establishing this work. And the one-day thing, hopefully in the future, we can do that. We are working toward that. It's not.
We need to have lines that we know are resistant. I mean, or whatever, right? So we can't be first at finding a new variants, right?
Yeah.
We have it to be second.
Yeah.
Right.
You mean that you want to be pioneer in that?
To screen it, you can't screen a new line if it was mutant. It just happened to show up.
Oh yeah. It is something that it is a long-term challenge.
Yeah.
So if you're thinking that we can have one kind of the resistant cultivar that can forever no, not in yellow rust and not in any diseases, because always. But the problem is here: some pathogens shifting very slowly. Some pathogens shifting very fast, and rust, and especially yellow rust, is one of them that is shifting very, very fast.
The other thing, Kaveh, there are 2 types of resistance. There are some sources that are more durable too. So, the breeders actually are doing a lot of work, and Rob can talk about it. But there are 2 sources of resistance. There are the sources that can break down easily, the old stage resistance, and there are the adult plant resistance, which actually we do this work. It's more like to look for adult plant resistance, which is the more durable kind of resistance that can last really. There are proof of it to last really long in other, like in case of leaf rust. So
Are occurring elsewhere in the world, though, right?
it does occur here and everywhere else in the world, and here since 2000.
I meant the changes, the variants, variants.
Virulence?
Virulence.
Virulence change, yes, everywhere.
Everywhere.
Everywhere, yes.
So if the people like to
She has a question.
Oh,
Sorry.
Yeah, so we have varieties that have been registered as resistant, especially winter wheat varieties, and we know that some of the older varieties that resistance has been breaking down. So is there any way, like it seems during registration, that gets an R rating at say 10 years down the road, it's NS. Does that rating ever change, or does it always just stay as a R?
They deregister from minus sometimes because the resistance break down and then have newer ones coming.
Yeah.
Yeah, no.
It's
So, but I like what you're saying
Yeah.
about the adult resistant. There's different types.
Yes.
So we're obviously working on plants that
Yeah.
will be better in the future.
Yes, and we are trying to bring more, like the breeders are trying to bring also combination of gene, because the pathogen can change against one gene. It take a time, like, but then to change against two genes or combination of that, it will take it more time. It probably eventually will change, but like then hopefully it's always like arm race, like you always racing against this pathogen. The one thing I have to mention, and I forgot to mention after, like I have to acknowledge a lot the source of the fund. I mean, Western Grain Foundation, they funded all these disease nursery, and I am so appreciative of them supporting our research. The Alberta Wheat Commission and the Saskatchewan Wheat Commission, they are supporting us in a different fund project for the race characterization and other work. And yeah, I thank them, because that's how we could hire our awesome staff. Yeah.
You were talking about the different races and virulences of the races, and if you were able to sample and have that race within one day, would that change economic thresholds of spraying if there was different races that would be more virulent than others?
It just will change the way we get communicated fast to the breeder what we have in our pathogen. You know, the breeders are always interested to find the effective resistance gene. If you can give them that answer after 1 year versus you give them, I don't know about 1 day, let's be conservative, within short time, I don't want to specify. But like if you can give them that answer very short, it make a lot of difference, you know. Aside from that, it cuts a lot on the effort. I mean, so far, the reality today, to do risk characterization, you have to do it on those lines. You have to infect, and as Kaveh mentioned, it takes about a month to do one. Now, you have to imagine, we have also limitation in our greenhouse space. We have to put them in certain condition. We have a space limitation. We can do per week about 10 isolate. To purify the isolate, you have to inculate almost 50 different pots just to go to the down one pustule, because this thing you see, the yellow thing, they might a combination of different races, and to any race characterization you had to get it down to like to the single pustule, and to get that purification already from one isolate you need like 1 month, and then to characterize it other 1 month, and then you know it take a year to characterize almost like a collection of 100 to 200 isolate, and it take a lot of hours and people working. So hopefully if we can use genomic tool to develop something that can assist us, not replacing this, but assist us in directing us to give us hint to a faster question, will be great.
Okay, I think we have to wrap it up. So, Reem, I appreciate your team's time, and if you can all join me in thanking her.
Thank you, guys.